So now we're going to look at 4 examples of machines from computing history that sort of lay out some of the ideas of modern architecture that we use today. A lot of the things that we use today were inspired by and continue to evolve from practices that emerged in the early days of computing, recognizing some problems and trying to solve them. So things like virtual memory and DMA and cache and microcode and superscalar, all these kind of things were, of course, developed at one time in order to solve a particular problem. And so I wanted to look at the machines that are representative of the first-ish standard way of doing these things. Again, these ideas emerged back and forth from the different organizations that were developing and deploying computing. But these 4 examples are examples that any computer architecture person, computer historian, or computer scientist should probably know anyway, so it's worth having a look at these guys. So first, the Atlas in 1962. This really was the beginning of conversations about different ways of accessing memory. Before this, there was primarily main memory, and there were registers, and there was sort of secondary memory with tape drives and stuff like that, but they weren't as integrated into the machine as they are in this, because this is the first time we talk about what today we would call virtual memory, but the Atlas talked about as one-level memory. This idea that you want to give access to each programmer. You want to allow each programmer to be able to access the memory space as if it was their own, and to give access to more memory than might actually be implemented, because these memory spaces, theoretically were quite large, but memory is very expensive and difficult to implement. And so if a programmer wants more space than is available, find some way to do that. And the innovation that they come up with is not all of the memory is used at all the time. And so if a programmer wants this information, but this information is maybe not being used right now, we can just put that on the disk, put that on the temporary storage, and bring in the information that they might need. And so in order to do this, the processor, the machine, has to translate the memory address that the programmer asks for into the memory address that is actually where the machine has put that data, because it's not going to be in the same place. We don't have all that place. We don't have all that space, right? So again, this is what the introduction of ideas of virtual memory, and it comes from the fact that the Atlas also recognizes 4 different kinds of memory storage, right? In this picture, we have operating controls, peripherals, tape store, drum store, vStore, which is sort of the virtual memory space, as well as the registers. And today, we sometimes forget that we have these different kinds of memory storage, and they can impact computer security in different ways. So we have, primary memory, which is our sort of main memory space, and then cache inherits from that up to registers. We have secondary memory, which is sort of our peripheral space, not the peripheral space, but secondary memory is, our long-term storage, our SSDs or our tape drives. Not usually these days, but disk drives, even the internet and cloud can be considered secondary storage. And then firmware, this is locations in memory where you store information that the user doesn't usually have access to and stays there from one power cycle to the next, right? So low-level operational stuff that gives instructions on how to control some of the hardware, all of this kind of stuff, as well as memory mapping our peripherals so that we can have access to them in a similar way that we have access to our regular memory. And later on, memory mapping becomes a standard practice, but this is an emergent practice here in the Atlas. It also recognized that because memory swaps are slow, moving information out of main memory onto disk and then some moving back in again, you can do other things while you're waiting for that. So this is the beginning of some early multiprocessing. So this one-level memory we call virtual memory gives access to a larger memory space than might otherwise be available, and then swapping out or paging out data from the memory into the secondary storage and back again. Before this, programmers had to do this manually. If they wanted to swap out memory, they had to actually manually write the code to move it onto the disk and come back. And the programmers had to place information in the main memory in clever ways so that they would have access to what they needed to do. Now the machine takes over that control. The machine puts stuff in the right place and then translates the memory address from what the programmer asks for to what the machine actually produces. Again, early multiprocessing, allowing this swapping out, and as well a little bit of early pipelining here as well. The machine would fetch an instruction and start executing it, and then the fetch hardware is not doing anything, so it would just go and get the next instruction while waiting for the instruction to complete. And today, this is what we see in pipelining, of course. The IBM System 360 in 1964, and again another link, it brings in ideas of buffer memory or cache, recognizing that when we move information from memory into the registers, memory is quite slow. We want to move a bunch of it at a time, but we won't need it all at once, and so we want to have another place to put it. So this is something between main memory and registers that we can bring information into so that we can use it in different ways. And then all of the challenges that come along with this, right? Recognizing that when we have data in a cache and in memory, it's in two places. And so if we change it in one place, we'd better make sure we change it in the other place. So this is called write through. We would write the data to the cache and also back through to the memory, slowing down writes compared to reads. And so recognizing some of the advantages that cache brings, bridging this memory speed gap between main memory and registers, but also recognizing the challenges, which is when you have copies of information, bad things can happen. So this was one of the big advances of the IBM 360 as well. The other big thing that the IBM 360 did, well, first of all, the other thing that the IBM 360 did was consistency across a platform. So before this, machines were separate, and even different variants of machines would have different versions of operating code and different ways of doing things. IBM System 360 said all of our machines are going to run the same instruction code. And yeah, that's going to make it challenging to do some things, but what it means is if you write code on that machine, it probably is going to run on that machine. And this was a big concept, recognizing that the code that people wrote was an asset to be maintained, as opposed to just writing code for a problem, throwing it away, and starting again. So that was a big thing that the System 360 brought in. System 360 also brought in microcode, which is a recognition that when an instruction takes multiple clock cycles to execute, each of those clock cycles has a bunch of control logic that has to make choices within the data path. And so you're going to have little bits of instructions that say what to do. Those become like a little program in and of itself. And so if you have, several clock cycles to do a add instruction or whatever, each clock cycle has a tiny bit of, ones and zeros that tell the machine what to do that portion of the clock cycle or the portion of the instruction. So we call this microcode. This is a very common thing today, and again, becomes a vector for attacks sometimes. But recognizing that the hardware execution, what the thing does in each clock cycle, can also be a language, and this micro language can be micro cached, and it could be micro forwarded, and all the kind of things that we do to regular assembly language, we can do with microcode as well, albeit in a much, much simpler variant. So some of the other videos I have about producing the hardware that can execute code, the data paths, some of those we'll talk about microcode as well. So these were some of the big advances that the System 360 brought in. This is an example of the microcode that would execute an operation. So this is several clock cycles, and each clock cycle would have individual control signals that would make choices, right? What does the adder do? What are the inputs from the adder? What are the, where does this piece of information come from? Where does the result go to? Does it get shifted? Does it get branched? So all of these little things are individual control logic that would choose, multiplexers or routing or whatever. But by establishing it as a code entity unto itself, then that leads to the opportunity to optimize that code and maybe even change it after the fact, right? Putting that into its own little memory and its own little control system means you can go back after you've built these machines and maybe tune the microcode so that different things can be done on the same hardware. So the other big thing that the System 360 did is recognize that machines are going to be in place for more than a small amount of time and might be used for something different than they were first deployed for. And so you might want to be able to come back after the fact and make some changes. The other thing that 360 did was pipelining. In the IBM 360-91 in 1966, and again, here's another link for it, bringing in this idea of concurrency among instructions. And in these days, they were talking about parallel processing. This is what they were talking about. You start one instruction and then you start the next instruction before the first instruction is done. So they called this concurrency among successive instructions. They also called this assembly line processing. And again, recognizing the benefit that this brings, because you can get more instructions done per unit time, but also the complications that it brings in the fact that then you have to pay attention to, does the inputs to this instruction depend on the outputs from that instruction? And so all of those kind of conversations began happening as pipelining started to be brought in.